Okay, so you have hopefully set up your coursework repository. So let's take a look at the actual coursework. And the file we're looking at is the one.agda in the coursework directory. So let me load that. And what we see is that we have a whole bunch of open goals. And it's your task to fill in these goals. So that's a little bit overwhelming. Then what you can do is you can go down to the problem you're currently working on. And then you start the comment, you go to the end of the file, you finish that comment. And if you reload, then you see that you only have one goal to fill in at a time if you do it that way, or more if you pattern match, etc. But hopefully that's a little bit more manageable then. But I'll comment that in again. Let's start from the top. So at the very top here, I've given you a bunch of things imported from the standard library. See that for most of these, I've actually told you exactly what can be useful from each file. So true and false and not and or etc. for booleans. So that could actually be a help for you because it means that anything else you don't have to worry about, right? You don't have to use all of these things, but you could use some of these if you want to find it helpful. For other things, such as string and characters down here, I haven't given you an explicit thing, so you might, when you want to use something with strings, you might want to middle click on this, which will take you to the file, and you can see what is useful things are defined in it. So words here and lines are quite useful functions, for example. Okay, so let's go back and let's look a little bit at the actual questions. So the coursework is divided into three parts, more or less. There's one first part on functional programming, so you might have done it mostly before. There's a second part on logic, which we'll talk about in week 2. And there's a third part, which is about half of the coursework, which is about building a program for manipulating grayscale images. So I hope that's going to be a lot of fun. But let's start from the beginning quickly. So in this bit here, I'm asking you to build up to a sorting function on lists of natural numbers. Yes, natural numbers for simplicity, which we're doing by making a tree and then flattening that tree again. So you can fill in these holes. Hopefully that should be relatively straightforward if you remember what you've done in Haskell. And then afterwards, if you want to make sure that you've done the right thing, you can comment out these test cases I've given you here. You can now reload. You see that Agda is not convinced that this is true yet because it's made this yellow, suspicious yellow, because I haven't actually implemented any of these functions, right? But if you do that and implement them correctly, then this is not going to be yellow and Agda is going to be happy. So that way you can unit test the program if you want. Okay, so then what we do next is we look at a variation of the flatten function, which is going to be linear rather than quadratic in efficiency. And we can use that to make a more efficient tree sort as well. And that's also something you could do in Haskell, but this next step you couldn't, because here we are proving that the two flattened functions actually produce the same results. So fast flatten equals flatten with this appendixes here. And using that, we can also prove that the two sort functions actually do the same thing. So we can prove that the fast version is correct with respect to the naive version. Okay, what about the logic bit? So here I'm asking you to prove a bunch of logical statements. And many of these are quite straightforward. Maybe you can even get Auto to do them for you, but not all of them, I think. And especially here, you have to be a little bit careful because not all of these are actually going to be provable. So here, I've already started to comment this one out, for example. It might not be this one, but so what I'm asking you to do is to either prove it or to comment it out like this and say this is impossible because of blah, blah, blah. So you have to decide if it's provable, in which case you should prove it, or if it's not provable, and now you have to give a reason why it's not provable. Okay, comment this out again. Okay, and this is the same idea. This is quite fun. So you can actually show that negating something twice has the structure of what's called a monad, which you might remember from Haskell. So that means that there is a return, which says that P implies not P. Of course, we don't have the other direction in general constructively. And we have a bind operation, which says that if we have not P, then here we can assume the underlying P, and if that proves not Q, then overall we prove not Q. So you're asked to prove this, and after you've done that, you get access to do notation for double negated statements. So that means that we can do things like this. We write do, and then write a sequence of statements where we can bind not knotted things and get the underlying P, so to speak. And this is all desugaring to this bind under the hood. Right? You can play around with that. You can make a hole here, for example, to see what is going on, perhaps. At least the types of the things involved. See that here we had a not P, and then we turn that into a P that we can use in the rest of the thing. And of course, we can only do this if we're also proving something which is not something else. So that's fun. And here I'm asking you to do that. Use either not map or do notation to prove some other facts. And the final thing in this logic section is trying to highlight something called the drinker's paradox, which is a paradox of classical logic. It's paradox in the sense that it is very counterintuitive. So we're assuming classical logic in form of the obviously the middle. And we're saying that, well, if there is a set of patrons, there is a predicate that tells you if a given patron drinks or not. And then the paradox says that if there is some patron P0 in the pub, then in fact there exists a specific patron P such that if P drinks, then everybody drinks. So P is deciding if everyone in the pub should drink or not, which you might not be so used to if you've ever been to a pub to actually find this patron that decides everything. But using classical logic, you can prove this statement, which is quite counterintuitive. Okay, so that's about half of the marks. And for the second half, we are writing a slightly more involved program, which is dealing with grayscale images. So that I've given you some examples of these things in the examples folder. So for example, here is a grayscale image of my cat. Here is the grayscale image of the Strathclyde coat of arms, Portincross castle, and a nice looking tree. So these are just images, but they're grayscale. And the point is to write now a program that can manipulate such images. So first, here's a description of how the file format actually works. And we can look at some examples. We have these actual files here. We're also given some string examples. So this is how it works. It starts with a magic header, which is always going to be P2 for all of these. Then comes the width of the image, which here is 24, meaning that there's 24 pixels on each line like this. Then comes the height, 7, because there's 7 rows here. And then comes the maximum value of any pixel. So you see that of all the pixels here in this raster, the maximum number is 15. And then comes a raster of all the pixels in the image with values ranging from 0 to this maximum value, right? Where 0 means black and the maximum value means white. Right? Okay, so that's how the file format works. It's called portable gray map. And we see that it's quite naturally a dependently typed format, right? Because these numbers here determine how many things to expect later in the file. So the first thing I want you to do, after meditating on that a bit, is to represent this as an AGDA record by adding in the fields here. So how can you represent this data as a record? It's going to be a dependently typed record. And then after you've done that, we can write a function which takes one of these records and turns it back into a string again, right? So we can then produce this string representation of the same thing so that we can talk to other people about it. Another thing we can do is if we have one of these, then we could also turn it into the image it actually represents using some ASCII art, right? So let me actually show you. I prepared this. So we have here the executable that we are producing. So if I do that, and I say the action ASCII, and I give one of the examples, for example, the Strathclyde logo, then it's producing this ASCII art version of the logo, right? We see there's some black, there's some white, there's some gray in the middle. So that's what I want this view function to do. So I'm using an executable that I did before I commented, turned this into a whole again. And I've done some very simple things where I decided what should be gray and what should be black, but I leave it up to you to see if you want to have more than just, so I only have white, black, and something in the middle. But you can have more than that, right? And you don't have to use these symbols. Maybe there's better symbols you can use. Okay, and if you have this function, then you can also run it inside Emacs by doing Control-C, Control-N, right, to normalize the expression. So you don't have to compile the program every time. Okay, the next thing I wanted to do is to be able to read one of these things. So take a string and maybe produce the AGDA representation of it. And I say maybe because not every string is actually a valid representation of an image, right? So we're not guaranteed to actually produce one of these. Whereas when we view it, we started with something we knew what it was. So we're always going to produce a string. And if you think about all of these, I haven't given you the individual steps you should follow. That's really up to you. So I'm hoping that you'll think a little bit about how to design a program to do these things. But of course, you can ask in the labs for help if anything is unclear, right? Okay, so if you implement this, then we actually have implemented enough pieces to have this basic program, because we can read a file, we can do something with it, and then we can also write it back again, right? So at this point, you should be able to actually compile your own version of this program. And if you go down to the bottom, you see the main function I've given you, which is already doing these things. And you can compile it either on the command line, or you can go to AGDA and compile like this. Choose the GHC backend, the Glasgow Haskell compiler. Except it's not going to be happy to compile it if you have any open goals in your programs. You might have to comment them out if you have these earlier ones, like this, right? Okay. So what can we do next? So now we can read files, we can write files. So we could put something in the middle that does something interesting to the file. So that's the next few steps. The first thing I'm suggesting you do is this poster version of a file, where if you have a cat like this, then the poster version is turning all the gray things into black and all the white things into white. So it's a more stylized version, right? So that's what I'm asking you to implement here with posterize. Next, you could also imagine to rotate the file. So if you have port and cross like this, if you rotate it, it should look like this, right? And you could also reflect the file. So if we have a tree like this, then reflecting it should add a mirror image of the tree at the bottom of it. So it will look something like this, right? You take this and you just reflect it in this line in the middle. And finally, okay, so that's the basic things I'm asking you to implement. but you could also, for more marks, do some extra bells and whistles. So the first thing is that the file format I described before, looking like this, is not quite correct, because in files you find on the internet, you also see that you can have these comment lines in the header, where a comment is anything that starts with a hash symbol and then goes to the end of the line. So here I'm asking you to strip these out so that you can download a random image and work on that as well. Right? You see that at the moment this is just defined to be the identity, which is not a very good implementation, but that's because it's already in the pipeline here when you read things. So if you implement this function correctly, then you will also be able to strip out the comments of the files you read. And finally, for the final 5 marks, I want you to come up with something else that's cool and fun to do. So you could be to blur the image, or to invert it, turn white into black, and vice versa. Or you could merge different images, or anything else you could think of. And again, if you can't think of anything and none of this sounds exciting, then you could also ask in the labs and we can help you come up with something. And you do this by implementing your function here and then hooking into it with this action, your idea here. Replacing this right-hand side with maybe something like what we've done up here. Right? Maybe change this your idea to what it actually does. And finally, I'm also giving you up to 4 marks for some good style and a good design of your programs, etc. So some good comments if needed, and so on. So yes, some marks for writing a nice program as well. Okay, I think that's it. I hope you'll enjoy and look forward to helping you with it in the labs.